Good morning, everyone. My name's Tim Keeping from the Geological Survey, and I'll be talking to you about the Mobile Petrophysical Lab that we organised through CSIRO, through Shane Mule and Cameron Adams. We got ourselves a thing called a Mobile Petrophysical Logger. We got this initially for the Gawler Phase 2 project, and we logged 48 holes. We also extended it to some other holes because we had about a few months left, so we went around Carapatina, Prominent Hill, and of course the Delamerian project from the year before. Now, the Mobile Petrophysical Logger, it takes 7 data types. This means for the people processing the data, you get up to 46 columns of data per line, thanks to the XRF, and we have in total over 12,000 lines of data from the entire state. Now, the Petrophysical Logger really just talks about the shipping container it sits in. That shipping container contains everything required to power and run and use what's called the multi-sensor core logger from Geotech inside it. It is deliberately designed so you can take it anywhere. So it's originally designed so they could take it out on a boat and put it on the side of an oil rig. But as long as you can provide the power and your own SIM card for internet access, you can put it anywhere you want. Okay, what's inside? In there is this multi-sensor core logger. So starting from the right-hand side, you put the core on the end and it gets slowly pushed through this device. The first device measures, we get some density. Using a cesium source, we measure gamma attenuated density. Then we measure P-wave velocity through acoustic logs. Then it measures some magnetic susceptibility in XRF. Then there's a loop mag-sus device, followed by a induced electromagnetic conductivity device, followed finally by the natural gamma. And sorry, in there is an XRF as well, just not on that picture. Okay. Now the problem is it's traditionally it's a slow device. It's made for use on the oil rigs where they'll only process a few meters of core a day. They'll pack it into a cylinder, and they're just checking to make sure the petrophysics they're reading off the core is the same as the petrophysics they measured in their downhole logs, and then they're drilling to try and work out where they are in their drilling program. For us, so this is a problem. It would take months to do one drill hole if you followed the traditional way of using these. So talking to CSIRO, they decided to decimate from 2 centimetre readings to 5 centimetre readings. And then we started alternating some of the readings because most sensors are quick, they're less than, say, 5 seconds, but 2 of the sensors take at least a minute each. So we started alternating the 2-minute readings, which is the natural gamma and the XRF, and we got a throughput from 5 metres a day up to 20 metres a day. So still that's pretty slow, you're still not going to get through an entire drill hole. So the next course was you've got to be strategic in your logging. So luckily in my case, I was following the geochemical samplers, so I logged about a metre's worth of core around every geochemical sampler that was taken as well. CSIRO came up with the idea, if you take enough of these small samples of logs within the same interval, you can just extrapolate it to the whole interval for your modelling later. And we'll be looking to see how well does that really work in this talk. So this illustrates what happened on the golf ball the golf ball hole. We took readings just coinciding with the geochemistry. As you can see, so you'll stop and there'll be an intense amount of logging for say 30 centimetres or 50 centimetres, and then you jump on to the next sample. Now using this, how much information does it really give you? Well, the fear was, okay, we wouldn't have enough info to be able to discriminate things, especially since we're using a soft rock technique on hard rock. How well would it really work? Well, I think it's not as distinct as the soft rock, like going from your clay to your sandstones. That's nice and gives some nice distinct changes there in your natural gamma, say. But in this case, there are changes, but they're very small. But I think you can see them, and I think we can show that they work at least to some level of scale. I don't know how small you'd really get it, but I think it worked well overall. The grey dashed lines indicate like a pathway of the average value within these units. This is a semite, Moving to peelites. Just happens to intercept also where there's a bit of gold mineralisation. So this worked out well. In Gulf Bore, we're able to show that there is a difference. It is slight, but there is a slight difference in the data types when you cross between the units. So if you were modelling, so you're doing inversions, machine learning, your own forward modelling, you could use slightly different ranges to build your models with and make a distinction between the units at that scale. So, as our test, pre-GP2, out of the 48 holes, 5 of them did not have published stratigraphic units at the time. So, could the MPL see them? So, I've split them up into 4 gross stratigraphic units. The biggest ones, of course, being the Christian ice and the Molgathing complex. I took the smaller collection of units, generally with much less readings, and grouped them all into what I'm just calling the generic name-aged units. And the unnamed are the grey drill holes up to the north, just to the northeast of Challenger. Okay, in this case, what I've done is I've just plotted the entire 48 holes worth of P-wave velocity in one line. But I've grouped it by their known stratigraphic units, so we can look at them quite distinctly and just see if there's anything going on. Now, I'll also talk a bit about the different sensors. So for the P-wave sonic log, it's very anticipated. It's a very in-demand value out there, especially with the large uptake of passive seismic and now ambient noise tomography. The problem with the logger is it's made for soft rock and it always has a cylinder that's the same size. We don't have that in this case. There's a lot of variation out there with drill hole size core, and once you start splitting core, nothing's the same size. So there's a lot of averaging had to be involved, and the device itself is quite sensitive to the core size, shape and condition. Any kind of crack or fracture or movement, and you suddenly get a drop. You'll just get a drop out of your speed. That's where all this noise comes from. So if we filtered out the noise, we still get a reasonable idea of what's going on in each unit. Unfortunately, not much variation in the P-wave, but okay, it's probably mostly because it's the noisiest value to try and measure. If we move to the mag-sus, there were 2 types of mag-sus, touch and an induced non-contact, so it just takes a magnetic response from a larger volume of core each time. So there's more variation here between the units. So we see Christian ice is a lot flatter. In fact, it's so flat, that's basically the same kind of reading I'd get from a sediment. Whereas the Molgathing, much larger, all-encompassing unit, there's much more variation inside it. Okay, that's pretty reasonable. And we can see that part of the unknown drops down to the Christian ice, probably an average level, whereas the average level of the unknown units is generally around the Molgathing domain. Now, natural gamma. Now, this had 3 scintillometers running for 1 minute, so you get the equivalent of 3 minutes worth of reads being averaged out. Wasn't expected to be particularly interesting, particularly on hard rock, but thanks to the magic of vertical exaggeration, and just so happens the 100 counts per second line, you can see Christian ice averages just above, Molgathing just below. And once again in our unknowns, we're seeing the same pattern again. Resistivity, again, this is a bit more problematic, particularly because you're dealing with the hard rock. In the petroleum situation, they've got the water in there as well, so they're going to get nice, distinct values. Here we had a lot of what we'd just call invalid values. The device is calibrated for only 0.1 to 10 ohm meters, so we had to cut out a lot of the values below, particularly just get cut out immediately. Now, we don't know yet if that just means they are more conductive and somehow should be included in the data set in a different way. But unfortunately, in the hard cap, they just get cut off. You see a bit of variation in here. You see some similarities. So Molgathing probably more associated with this unknown strat unit. The Christian ice, a lot of values were invalid for this graph. Same with this end unit again, so maybe another indication. If we put it all together, it turns out these are drill holes from the Acacia prospect, they're all at this level. This is Gulf Bore. So it looks like you could draw an inference that the Acacia prospect is Mulga thing, Gulf Bore is Christie Nice, and then of course the geo said, well, we already knew that, thanks. But it at least shows that you can see something in the petrophysics in hard rock, which was one of the main goals of this pilot program. Okay. So let's try and explore it a little bit more, see if there's anything else we can tease out of this. So I went to just the Mulga thing, because that's the all-encompassing strat unit. Can we break it down anymore? So we're using the 3 drill holes from Acacia prospect you saw before, and 3 drill holes from a Dominion mining PACE project from the 2000s. Now, in this case, they're coloured by whether they're felsic or mafic, felsic being orange, mafic being red. So there is some variation, but more interestingly, it turned out the variation is actually more locational. When we look at the felsic itself, okay, you're seeing more variation in the Dominion mining area than the Acacia prospect area when it comes to your natural gamma. Your mag sus seems to be higher in your Acacia area. When it comes to the mafic holes, same again, you're getting a lot more variation in the Dominion mining area with your mag sus than you do with your Acacias. Now there could be a bias in there that there's a lot longer holes from Acacia, therefore more readings, but generally we're just not seeing that level of variation throughout the holes. So you could take this and go and look back at the holes and say, all right, is there something different in these areas that I should be thinking about? So you can try and use hard rock petrophysics in the same way you use soft rock petrophysics, such as water bore logging and oil logging. Now, early on, we were approached by a couple of companies who were interested in using the results for themselves. Barton Gold had just revised the Tarcoola area. They had high size relook at the Tarcoola area for a prospective seismic survey. So we put through a couple of holes for them, most notably Wilgena 1, which is nearly 1 kilometre long. And we were able to tell them, okay, you can expect the first kilometre to be quite boring. So quite predictable, basically. So they would have been able to use that in some way when it comes to their interpretation, particularly with the pesky top of holes, which are usually a bit unknown, because most seismic only concentrates quite deep. They pay almost no attention to that top few hundred metres. In mineral mining, though, you're going to have to pay more attention to those because you're not going as deep as petroleum. Hillgrove also approached us because they're chasing a conductivity target to the north of their Camman 2 pit. So they provided us with a drill hole with lots of nice conductive sulfides in it. They've been doing many surveys, particularly they've done an ambient noise tomography, a passive seismic survey, and they've been doing MT models, EM surveys over the district as well. So ultimately, how can you use the petrophysics? Well, we've shown that you can use it in the traditional downhole sense if you want to, trying to connect different lithologies. But in particular, we deliberately did this to coincide with geochemistry to maximise the value add of all the data we're giving you from this project. So you will have petrophysics that coincides with known geology, that coincides with hard geochemistry coming out of laboratories. You can then combine that with all the XRF that does come with the MPL as well for your own tests. And then, of course, there's the geophysics. So you can make your forward models. You can use P-Wave to create models like in the bottom left. That's a result of the Hillgrove ambient noise tomography survey. We have gravity and mag inversions, of course. Then we have an MT survey. So there are more and more electrical models being created out there, particularly in inverted. So understanding your resistivity would be beneficial. And then, of course, we get machine learning, where you theoretically can throw everything into the one bucket and it tries to tell you a relationship. What you want to do with it is up to you, but it is a method to try and use everything at once. And ultimately, these are all going to join together, and we're going to get better and better 3D models straight from inversions using things like machine learning. So you get, for 48 drill holes, you get measurements co-located with geochemistry and HiLogger. That's about 4,000 rows in the GP area alone, with up to 46 columns of data. And that processed data will be available on the same website next week as Anna showed you earlier. Thank you.